them, I would like you to ask questions and prepare some problems from before. So if you got them, let's just go through them. If not, I'll go back to these ones. So I hope you have prepared some problems.
Oh yeah, 1, 2, 5.
The question is, when is the first exam? I haven't figured that one out. Let me answer that next time, because I meant to do it today, kind of go through calendar, but I ran out of time for it. And I can tell you this, we finished modeling of the continuous time system. I plan on going to the discrete time, and then there will be a midterm exam. So probably a few lectures, a couple of lectures, or 3 or 4, to go through maybe 2 weeks to go through the discrete, and then 1 week for preparation and a second review session. So expected at the beginning of February. Beginning of October. The next one is going to be in the first part of November, and then in December you're going to have finals. So that's kind of approximately. I'll give you the dates next time, or when I go to the.
So can we take first one in the middle of the October?
It is what it is.
Yeah, because the course is pretty much so.
What is what?
Like
The
course is pretty lengthy for first one.
Yeah. 1, 2, 3.
1, 2, 3, yeah. So if it is in the middle of the October, that will be good for us.
So if you take it up to
It's more dictated by what's logical, you know, in terms of material. I'll give you a date. I'm thinking right now October 11th. That's the one that would be preferred.
October 11, yeah.
For
For the test.
the test, for the midterm. I think that would be okay. But I haven't worked out that one, so don't hold me accountable. So let's go. I have the first problem is 1, 2. Problem 1, 2, 3.
1, 2, 3.
Yeah. 1, 2-3. And it says express signals x1 of t, x2 of t, x3, and all the way to x5 in terms of the signal x of t. So here's how x of t looks like.
You took Joe's word on that.
1. This is 1. X of t. And let's just do a couple of those. First one, x1 of t. That looks somewhat like this. 1, minus 1, 1. All right. So the question here, I'll go through the rest of them in just a second. But let's see, how do you solve these problems in general? There are 2 steps to solving this kind of problem. The first one is not mathematical at all. The first one is just a simple, I would say, Lego problem, right? Like a 6-year problem. Can I build this out of this, right? And how do I do that? And the way how I would see, let's say one way, there's always going to be multiple ways, but one way how I can build this x1 of t, I can take this and put it here, and then I can say, take the same thing, flip it, and put it on the other side, right? Yeah, so now that I realize how I'm going to do that, now it's a matter of your mathematical skill, how you build that. So if I do this first, x of minus t, how does that signal look like? This is flipped to the other side. So this is x of minus t, right? This is t. So you see, if I take this one and I delay it by 1, what do I end up with? With exactly this right here. So I can say right now x1 of t is going to be x of minus t minus 1, right? To give me this half. So that's the one part. And I can put 1 over this. Now, if I look at this one here, this is same of x of t, but I have to advance it by 1. Right? So I have plus x of t plus 1. Right? So this is the second part. And then you end up, you just tidy this up a little bit, so this becomes x of t plus 1 plus x of 1 minus t. That would be one way of it. So let's take a look at, is it clear?
Yep.
Yeah. So let's look at a couple of more examples. Let's take a look at x2 of t. x2 of t is a square pulse that looks like this. t is between minus 1 and 1. Yes. Minus 1 and 1. And this is x2 of t. Now the question is, how do I build this one? Well, here are the, let me see. You can do that multiple ways, but let me say that this x2 of t consists of this one, because I already did this one upstairs, and then plus, what do I need to add to this guy? So I need to add this, and I need to add this, right? So this is minus 1, 1, t, 1, minus 1. Do you see that if I add this one to this one, I get this one, right? Okay? So now, this one I already built. That's this guy. How do I build this one? Well, let's call this x1 prime of t. Well, x1 prime of t, I can see that as essentially x of t on this side and x of minus t on this side, right? So I can say that this is x of t plus x of minus t. And then you see that x2 of t is equal to whatever I have here, x of t plus 1 plus x of 1 minus t plus x of t minus plus x of minus t. Right. So this is me building it without any stretching, right? I could have, just to illustrate, this is the solution number 1. Solution number 2 could have been something like this. I can see this x2 of t as consisting of, so this is minus 1, 1. One of them looking like this, and the other one looking like this, right? Would these two give me the same waveform, right? Add these two dotted ones together, right? Now you can see that let's call this one now x1 of t, and call this one x1. I shouldn't call it x1. Let me call it differently. Let's call this y1 and y2. So you can see now that x2 of t is equal to y1 of t plus y2 of t, right? But then what is y1 of t? y1 of t is this same pulse here, but it's stretched. How much is it stretched? 2t. It's stretched by twice, right? 2 times. But it's not only stretched. It is shifted, right? So if I can start by saying y1 of t is going to be x. I can say t over 2. That would stretch it to the length of a 2. So it will go from 0 to 2, but I need to advance it by 1, right? So I need to say x of t plus 1 divided by 2, right? Do you see that?
So should we first scale it and then shift it? x of t by 2 plus 1?
Is it?
Well, you scale it, right?
Scale.
And then it goes from 0 to 2, right? But then you shift it by taking, instead of t, you put t plus 1. And then you finally is the check. At t equal to minus 1, what should be the value of y1? 0. So if I put minus 1 plus 1, 0 over 2, 0, x of 0, 0. So it's the right starting point. At t equal to 1, what should be the value? 1. So 1 plus 1, 2, divide by 2, 1. So x of 1 is 1. Right? So this is y1. The same thing I can do with y2. Let's say, what is y2? y2 is this guy here. So it is x of minus t divided by 2. But then instead of t, I need to substitute t minus 1. Right? So it becomes x of minus t minus 1 divided by 2. And then finally check again. You know, when t is equal to 1, this needs to be 0, so t minus 1 is 0, x of 0 is 0. When t is equal to minus 1, then this is minus 1, minus 1, minus 2, minus becomes 2, divided by 2, 1, so x of 1 is 1. Right? So now, using this, you can say x2 of t is equal to x of t plus 1 over 2 plus x of, I can say 1 minus t over 2. Right? So that's another way of solving this, right? Both of them are valid. You know, it's just how you see these aggregate waveforms.
But is it the same answer?
Huh?
Is it the same answer even you have a different calculation?
Yeah, it is. It is. Yeah, it's the same. And then the final check is you build this function in MATLAB. It's very easy to build.
Yeah.
And then you test it. You know, you feed it 2t plus 1 or whatever, and you test it, and you plot it every time. And you can actually, if you get the same plot, then you're okay. Any other, I mean, there's a couple of other problems. I mean, they're all solved the same way. And should I just move on?
Can you do the C one? This is the one with the export T.
Export,
Yeah.
okay.
Yeah.
Come around now.
Okay.
That's a tricky one.
Well, you know, the trick here is really in the first part. Can we come up with a nice way of viewing this? Right? Then math is just a matter of a little bit of skill. So this is 1, so it goes to minus 1 over 3.
You got a first one, you fix that. You fix that, lower the small one, goes down
All right, so this is x4, so this is minus 2, 2. And this we call x4 of t. Okay? I know you've tried this before, so any suggestions here?
We did the same like we did over here, and then we subtracted a third one that was only a third high.
Go to something for the x1 and you flip that.
How about if I do this? I realize that this is essentially this, right? But subtract 1/3,
Scale
right?
that.
Right? You realize that this is. Now look at this first one. This is what? This is 1 plus 1/3, so 4/3 at this point. Okay? Now, this guy, I already did. It's x1 of t, right?
Right.
But now stretched
Stretched.
Yeah.
2 times, right?
2 times.
So I can say x4 of t
x1 of t by 2.
is x1 of t divided by 2 times 4/3, right? Because I have to scale it here. to make it magnitude 1, and then minus 1 over 3. Does that work?
Yeah, that's too easy.
Go ahead.
For x1 of t, would it be x of minus t plus 1?
Maybe I copied wrong. Where?
x1 of t on the left.
X1, this one?
Yeah.
So minus t plus 1. Yeah, that's what I meant. Minus t plus 1.
Minus t plus 1 in brackets.
Yeah, but
In the
when you,
parentheses.
minus t minus minus 1 is plus
T
1.
minus 1.
Yeah.
No, t plus 1 in parentheses. The
Minus
minus
parentheses
t plus
t
1.
plus 1.
Here,
Yeah, it's correct.
Yeah,
it's the
okay.
same thing,
minus t plus 1 is this.
Yeah.
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 I need to delay it by 1.
Delay.
So you
Right.
need to-
No, but you started off with x of t.
I started out with x of, this is x of minus t. And then I need to move this over here, right?
Why don't you shift
So
first
the
and then
plus sign.
flip?
Mm.
If you shift first and then flip, you get.
Okay, let's do that. Let's shift first. So this becomes, you're saying do this.
No,
Take this and shift it to this side,
Yes.
right?
X equal to 0, you will
So
have
then I
to-
have this signal, this guy,
Mhm.
right? And this is x of t plus
Plus 1.
1.
Right.
Then I need to flip it. So wherever I see t, I put minus t. So when I flip it, I end up with the same, okay, so where do I flip it? Let's say I flip it here. So I end up with this, but this is x of minus t plus 1.
Doesn't the negative go throughout?
No.
No,
Outside of the parentheses of t plus 1?
no, no. How do I flip? Instead of wherever I see t, I put minus t. I don't touch the rest, right? I don't touch the rest. So, and then the final test is what I did. You take the two endpoints and you test it. So if I want this, let's say, when I substitute t equal to 1, then it better be 0. So minus 1 plus 1 is 0. X of 0 is 0. So this point is okay. If I put 0, I have x of minus 0 plus 1, which is x of 1, which is 1. So this point is okay. Right? So it's the same. But you see this, and this is the same. Right? You know, the difference here is in the two ways how we got to this. Well, in x2 there were difference. Well, in x1 we are pretty much the same. But in x2 we had two ways how we got.
Excuse me, Professor. Does the shifting actually affects the power of the signal?
No.
No.
No, because remember, what is the power of these signals?
Same in the
Area under the curve.
under the
Very
curve?
careful. What is the power of these signals? Okay, average energy per time, that's definition. But what is the power of the signals?
Zero.
Average power.
Who said 0?
Zero.
0, because these are energy signals. They exist in all of them that I drew so far are energy signals. They exist only in a portion of time. So average per time, is 0, because the time goes, what did we say, forever.
So it doesn't affect if you stretch it, if you scale and shift that, so it will be the 0 like that.
Yes, but the power,
The
Power.
energy is what you mean.
Yeah.
but energy also doesn't affect if you shift it, and it is affected if you scale it, right? Because it's area under the curve. Like for example, when I scale it, right? Like, well, what would be a good example? Just take one of these, right? One of these triangles has a bigger energy than this triangle, right? Because the area under the curve. But in general, time shifting cannot affect power or energy. Why? Because remember, time, where I put 0, is usually at my discretion. This is where I count time from, right? So it cannot change the power. If I can, it's the same signal. If I didn't do this, it's the same signal. I might as well put 0 here, and nothing will change. Right? The area and the curve stays the same. So the power and energy are not affected by the time shifts. Okay? Any other?
Did you do 1
1.25.
1.25. Let's try.
Is that the freeway for the X1? Yeah, it's.
Makes sense.
1.25. Define 2 of x of minus 3t plus 1 is equal to t, oh my god, times u of minus t minus 1 minus u of minus t plus 1, where these u's are step functions. And it says plot 2x. So part A is plot 2x of minus 3 plus 1. Okay, that's an easy part. And then part B is plot x of t. All right, that's a hard part.
Yeah, the B.
Part B. So let's do first the easy part. Part A, it says plot 2x. Essentially what you need to plot is this. So what we need to plot is t u of minus t minus 1 minus u of minus t plus 1. Right? So how does this look like? Well, you can see this one, one way how you can write this is u of minus t plus 1 minus u of minus t minus 1. Right? So we have this one is easy. T is just going like this. But this is a u function that is going in that direction. And you see, when t is between, when t is greater than minus 1, right? Then this here is positive. Therefore, minus that is negative. Therefore, u is equal to 0. So this is, if you plot this, and you kind of police me here, because this is that pulse. Right?
Yeah, the minus 1.
How do I check? Let's check a point. Minus 2 plus 1 is minus 1. Minus is going to be 1. So at minus 2, it has to be 1. Right? And if I put 0, 0 plus 1 is 1. U of minus 1 is 0. So it has to go through these 2 points. And since it's u function, I'm okay. I already checked 2 points. I know I'm correct. Now, let's take a look at this guy here. This is an also u function that goes in the other direction. But when t is, let's say, greater than 1, the t minus 1 is positive. Therefore, minus that is negative. So this one starts from 1. Right? So this is the other one. So let me kind of label them here. This is u of minus t minus 1. And this one here is u of minus t plus 1. Right? So now the difference between the two, you're taking this one minus this one. So you see that below minus this one looks like this, right? So this, what I have downstairs, is minus u of minus t plus 1. So this one minus this one, you can say before here, it's 0 minus 0, so it's 0. After, between these 2 points, it is this pulse. And then after minus 1, it's 0 again. Okay? So now, multiply this and this. Here it is. I wish I had multiple colors. I know you might have blue one. All right. So Did you follow the steps?
Yeah.
Right. So that's the first part.
Can
Let's
you
see.
do that algebraically? I mean, like you put into minus t minus 1 u and you divide that.
Maybe you can do it any way, you know, it suits you as long as the result is correct. I don't know. But let's look at the part B.
Good luck, do it yourself.
Now let me just do it here. Let's try to do it as he suggested, algebra. We're just using algebra, right? So we have that 2 of x of 3 minus t plus 1 is equal to that. So the question is, what is x of t? What bugs me here is that the argument is not t, right?
Yes.
So let me do this. Define u, or not u, is of x equal to minus 3 plus 1, right? Then from here, t is going to be x minus 1 divided by minus 3, which is 1 minus x over 3, right? Follow so far?
Yeah.
Now, if I rewrite this one here, I can do something like this. X of no, let's not make this x. Because it's substitution. Instead of x, let's do z. Z, z. So I can say here, x of z is equal to 1/2, and then instead of t here, I can write 1 minus z over 3. Okay? Times u of minus 1 minus z over 3 minus 1 minus u of minus 1 minus z over 3 minus 1. Or plus 1.
Plus one.
Sorry. Plus 1. So far, so good?
Yeah.
So now, let me introduce another substitution, z equal t. Just trivial substitution, right?
Z over t.
Z is equal to t.
Oh, z.
Yeah.
Just change the
Yeah,
letter,
that-
right? So you have x of t, that's what I want, right? Is 1/2, 1 minus,
t.
let me pull this 3 outside. So this becomes 1/6, 1 minus t, right? That's what's here. And then let's see, what do I have here? I have minus,
1 plus z.
minus z, so it's z over 3. And then I have minus, well, let me actually put everything upstairs. So this becomes z minus 1 minus 3. So it's z minus 4. So it's u of t minus 4 over 3, right? Minus u of t minus 1 plus 3. So it's t minus 2 over 3. Okay? And then I can do this
It
here.
should be t plus 2 over 3.
Hmm?
T plus 2 over 3.
Because
Plus-
t minus 1 plus 3 is t plus 2.
T plus 2 over, yes. And this is 1 over 6, 1 minus t. And this is u scaled by 3. Well, scaling of u makes no sense, right? Because u is infinite anyway, right? It's u over t over, in other words, saying u of t is the same as u of t over 5, right? Because you can see, this is just triggering when t is positive, right? And it's positive whether it's 1 or it's 1/2 or 1/5 or whatever. So scaling of u doesn't do anything, right? So you can make this u of t minus 4 or minus u of t plus 2. Okay? And now we're ready to draw. Okay? I'm just going to use this part of the board. So we have a product of two functions. One is 1 minus t. That one goes through 1 when t is equal to 0, and through 0 when t is equal to 1. But I have to scale it with 1/6. So instead of calling this 1, I'm going to call it 1/6, and this is 1. And this is 1/6. This line here is 1/6 over
1 minus
1 minus t. Thank you. 1 minus t. Okay, so that's this guy. And this is just another pulse. It starts, okay. Let's imagine that this is 4. And this is the pulse that starts at 4 like this. And then I have another one that starts at -2, but it's flipped, right? -2. So this is this one. So I have to take this minus this, right? So before any one of them kick in, this is 0. Then at this point, it follows this until this point, and then they turn off each other. Right? So that's the pulse. So I have to multiply this with this. This will just flip the sign of this. So it will go through -1/6 downstairs. And then it will go this way, you know, from this pulse through this all the way to here, and then it will go. Right, it's not the most precise, but you follow the. So it kind of goes this way, then it kicks in, then it kicks this, and then it is turned on. Okay?
But actually, from the MATLAB that I plotted, it should be 1 and 1/2, not 1/6.
But that's probably the peak,
Yeah, but yeah,
not at the y-intercept.
no, yeah.
Well, you know, this is approach. I might have made some mistakes, you know, so just see what I do, probably catch some, you know, where I'm editing here live, right? By all means, go test it. But this is how you do this kind of problems, right? The key thing here, I don't know if you realize, you should have kind of said, aha, right away when I did this. Right? This is what did it all, right? Because I took whatever bothered me, made it a substitution, obtained t from there, and then substitute t with the rest of the stuff.
The problem we had is we took the original signal, and then we just tried to walk backwards with the shifting and the flipping.
Yeah.
Like in the A.
Yeah. And that's where it becomes complicated. That's why I went this way, you know. The trick here is you look at what's bothering you, what you're trying to, and then you work the other way. You say, okay, I want x of t, and you know, then let's calculate what the other things need to be. And this is what I meant, what I understood when you say let's do it algebraically. Just
Yeah, we got a different answer. We do that done in the algebraic and the like that you did in the A, Professor.
Because the orders of operation change, whether you shifted first and scaled, or
Yeah.
scaled first and shifted.
Yeah.
It's kind of tricky because you need to do that over properly, or like which one that you going to do first, like scaling or the shifting first.
Well, the thing is, you know, you should get always the same result, right? So if you don't get the same result, oh, it's all over, right? You start all over until you get two that agree reasonably, right?
You're not gonna get the
Sir, how
y-axis, right?
precisely are we expected to draw the diagram in exams?
How precisely? Well, just like I'm doing it here, label the points, right? If I were to do this exam, I would redraw it, make it scale properly. I mean, this is 1, I would do 4, you know.
And are we expected to get the exact intersection of that 1/6 straight line with that
Yeah.
unit pulse? Sorry, unit state?
It should be good enough so that I understood what you're trying to say, right? Remember, we're pretending I'm your boss and you're my employee, right? So you want to do it right so that I look at it first time and I say, okay, let's move on. Right? The trick about exam is you want to be as detailed as the time permits, because there is no immediate redo, right? I have to interpret what's on the piece of paper. And although you meant, and although it's on some other paper, and I was thinking, really it's what it is on the paper, right? Okay. Any other? 136?
136.
I'm still tripping out by that triangle. Can't shift and then flip.
Yeah, but you need the parenthesis, right? You worry about that, you are confused about it.
You can shift there and flip, but it doesn't work. Right in the touch. We'll see. You try to do it graphically.
Okay. It says let y so it's 1.3.6 or dash. It says y1 of t is equal to y2 of t, and it's equal to t squared. But this is only true when t is between 0 and 1. Outside, these two functions can be anything, right? So part A, it says define y1 of t as even and periodic signal with period t1 equal to 2. Sketch y1 of t and determine its power. Sketch and determine power. Okay? So let's first do it. So here's what I know. This is t. This is y1 of t. This is 0. This is 1. And I know that between 0 and 1, y1 of t looks like this. This is also 1, right? Outside of this, I cannot claim anything. But I know that y1 of t is even. Since it has an even symmetry, I take this, flip this over, and I know that on the other side, it looks like this. And then I'm given that t1 of the period of y1 is equal to 2. Since what I have here on the board is of the length of 2, I essentially know the entire function. I know that if this is now 2, this is 3, the function is going to look like this. Right? And this is, it will continue. Minus 2, minus 3. It looks like this. Right? So that's y1 of t. Now it says determine its power. Power, since it's the periodic function, all I need to do is integrate within one period, right? Yeah. The area of the curve and divide by the period. So, but since it's even, I don't even have to integrate over the entire period. I'm going to integrate over half a period, multiply by 2 and divide by the length of the period. So it becomes 2 times integral from 0 to 1, y1 squared over t, divided by period, which is 2. Okay? dt. Did you follow this?
Yeah.
Yeah. So 2 and 2 cancels, and this is integral from 0 to 1. y1 is already t squared, so this becomes t to the 4th power dt. So this is t to the 5th power over 5, divided, going from 0 to 1. So it's 1/5. 1/5. That's the power. Okay? Let's take a look at the second part, B. B. It says, design an odd periodic signal y2 of t with period t2 equal to 3. So I'm looking y2 of t to be odd and periodic. And t2 has to be equal to 3. And power equal to unity. Fully describe y2 of t and sketch the signal over the at least one period. Okay. I guess design an odd periodic signal, I guess starting from y2 of t, right? That's how I understand. Because y2 of t is given, right? So, okay, so I need a periodic odd signal. And power needs to be equal to unity. So this is t. This is now y2 of t between 0 and 1 is given, right? And this is this guy. So this is 1. Now, since I know that this needs to be odd, the part between 0 and -1 is fixed, right? And it needs to look like this. Okay? Right? And I need it to be the total area under the curve needs to be equal to 1, right?
Yeah.
So now, how do I do that? Well, if I just leave it like this, what's the power of this signal?
0.
0.
No. I extend it periodically. So here it's 1.5, and there's minus 1.5, right? I still don't know what the function looks like in these two intervals, right?
1/5.
Yeah, I need to. But
You have to
if I take this, square it, and integrate it, and divide by period, what do I get?
1/5.
1/5.
No.
1 over 5.
Period here was 2.
2.
So it will be 3 here. So it becomes 2/3 of 1/5. So it becomes 2 over 15, right?
Yeah.
You follow?
Yeah.
2 over.
So if I look at just the part from here to here, it would have power 2 over 15. How much more do I need? I need something that will give me 13/15ths, right? And the easiest way to do that is to say, well, I'm going to give it half here, obviously half here. So it's 13 over 15. So it becomes half of that is 7.5 over 15. So it's say again? 13 over 30. So there's a 13 over 30 here. The length is, so the power of this part here is going to be 13 over 30. But this is going to be equal to 1/2 times whatever is the function squared, right, in that interval. And I'm going to make it a constant. So this is going to be, this square becomes 13 over 15. So I'm going to make it like this. Square root of 13 over 15. And then here, minus square root of 13 over 15. Right.
I'm sorry, Professor. Why should become 13 over 30? It's not should be like 13 over 15, right? So it will be 1/2.
Because look, there's 2 over 15 here. So I need total of the power that is equal to 1. So it's 13 over 13. But I have it in here plus in here. So I have 2 of them.
Oh.
So 1/2 of 13 over 15 is 13 over 30, right? That's the power in this section here. Right?
Right.
But the power in this section, I'm making it easy. I'm just making the y constant, right? It's going to be the area under the curve of the square. It's 0.5 downstairs times the square, right? And the square is 13 over 15, right? So I take the square root of it. That's by no means the only solution, but it's just one solution. And these numbers, I don't like them. You might want to double check if, you know, you don't encounter square root of 13s and 15s often, but maybe they're correct, right? But that's the approach. Okay? And the last one says, I would double check them, right? So, because they look fishy. And which one? This is 1.3-6. Part C. We create a complex valued function, y3, determine whether the signal is periodic. If yes, determine the period t3. If no, justify why the signal is not periodic. Okay, so you have two signals now. This is the signal y1, this is the signal y2. We form the signal y3 of t, which is y1 of t plus j y2 of t. Is this signal periodic?
Yeah.
It is, right? How do I know if the signal is periodic? This is now, forget about this is complex, right? You are adding two functions, periodic functions. The periodic, one of the problems I think that I gave you for homework, actually, or that I've solved, actually I solved it in this note. So if you're confused, look it up after the class. But if you add two functions and both of them are periodic, and you have the period of the first one is t1 and the period of the second one is t2, then the sum of them is periodic if t1 over t2 is equal m over n. If the ratio of these two is a rational number, right? So, you know, and in that case, their period is, I guess from here, you can say that, and it's easy to see. When does this repeat? If I have n periods of t1, that has to be equal to m periods of t2, right? And that's when it starts again, right? So if it happens, if I go n times t1, and I get to the same point by going m times t2, then I can move the 0 to that point and start over. And in this case, the period t is going to be either n times t1 or n times t2, right? In our case here, t1 was equal to 2, t2 was equal to 3. So I see that t1 over t2 is equal to 2 to the 3. So the period t is going to be either 3t1 or 2t2, which is 6 in both cases. And it's easy even to picture this. You're going to, let me try to draw it really quickly, but you see what happens. Really easy. So this is 1, 2, 3, 4, 5, 6. This is the first one. Right? And the second one looks a little bit more funky. Goes like this, and then like that. And then gonna be, so 1.5 here, okay. It's not gonna be easy, but let me just do this. I know that the period is 1.5, so I'm gonna do this. This is 3. So this is 1, 2, 3, 4, 5, 6. So this one will somehow go like this and like this here, right, in one period, and then another period it's going to go like somehow like this here, and then here you end up, right, at the same starting point. Here they align, right? So this pattern and this pattern meet every 6. This I didn't draw really, right? It kind of looks like this, right? Here and then. Right, and then okay? And then the last one, determine the power of y3 defined in part C. Now the power, we went through that in a class, And we saw that the power of the complex function is the power of the real part plus the power of the imaginary part. That these two don't mix, right? So we already kind of did that. Power of the second one is 1. Power of the first one is 1/5, so the sum of the two. All right. Next one.
1/5 here.
1/5. 1/5. Which one?
1/5 here.
12. Was that one assigned?
Yes.
Okay. It's not marked in this book, so yes, I know which one you didn't do. All right. So 1/5/12. We have a complex signal x of t, which is equal to t squared 1, t squared plus 1 times z. Over an interval, t is between 1 and 2 inclusive, right? The remaining portion is defined such that x of t is a minimum energy skew Hermitian signal. Oh, okay, so I see. I didn't really talk about it, did I? Is this the right problem?
Yeah.
Okay, that's skip this one.
You could. Right now.
Huh? Because I didn't really define what is meant by Hermitian signal. Just skip it, just erase it from the list. All right. That's neat. Which one?
1/5/12?
Okay. 1.46. It says, find and sketch integral from minus infinity to t, x of dt for the signal given in P1 4-6. Okay, so there's one. Okay. So it says, let me define y of t as an integral from minus infinity to t, x of tau d tau. And this is how, well, let me just do it since we're loose anyway. And we have part A and part B. Part A looks like this. 1, 2, 3, and then here we have an interesting event where it's a delta function with area under the curve equal to 1. And this is how our function looks like. It is a pulse, and then another pulse here. And this one you can integrate without thinking too much about it. So this is 1 and minus 1. So if I start, imagine me integrating from the left to wherever I reach at the point. Up to this point, I'm integrating all zeros. So I'm not doing anything, right? After this point, I'm integrating u of t. What is an integral of u of t?
T.
T times u of t, right? That's an integral of u of t. So it goes like this, right? So now, at this point, another one starts kicks in. This is another one, but this one will drop. Whatever I integrated here, it should be clear that by this point it's gone, right? Because the area under the curve from here to here is just the opposite of the area under the curve from here to here, right? So you see that up to this point, I hit 0. And then from this point, I'm integrating negative, so I'm going to reach this point. Okay? So this is the area of these. Now the question is, what happens at this point? Up to when I'm at 0 minus, or actually 3 minus, right? My value is minus 1. So I have accumulated initial condition minus 1. When I transition to this point, I have to the right of this 3, I have integrated another delta. What's the integral of this delta? 1. So I had to add 1 to whatever was my initial condition. My initial condition was minus 1. So when I add 1 to minus 1, it's 0, right? So here the delta is discontinuous, and then after that it stays at 0. Right? So look at the qualitative difference here. The difference is you integrate, when you integrate the finite value functions, integral is continuous. Like look at this curve. It changes, but at every point it's continuous. Right? It's on the left-hand side and on the right-hand side are the same values. But when you integrate delta, you get jumps. Right? You go from minus 1 to 1 instantaneously. So here is the point of discontinuity. Right? Okay? But it's relatively easy to understand, right? Okay, so let's take a look at the next example. Next example has something like this. T, and then it has a u of t, and then it has all of these deltas that are occurring at integer increments. Maybe this one does not exist, so let's not put it in there. So this is 1, 2, 3, and then the area under the curve from each one of delta is minus 1. That's, I assume this is the notation. Okay. So let's just actually keep it like this, because it's more interesting if these deltas don't continue. You just have 3 deltas. So before 0, it's 0, right? Because you're integrating essentially 0. At this point, you start integrating step function. Integral of this u of t is t times u of t. So you go up to this point, and you hit 1. At this point, you have a 1 accumulated. But you integrate delta that has the area under the curve minus 1. So when you add the 2, this brings you back to 0, 0. So this kind of falls back down. There is a discontinuity instantaneously. On the left-hand side, you're 1. On the right-hand side, you're 0. Now this happens again. Right? You continue integrating this guy, but then this brings you on down. Integrate this, brings you down. But what happens here? This, right? Because after there are no deltas anymore. So you keep on just integrating u of t as if you started from u of t minus t. Right? So from this point on, you just keep on integrating with the slope. This is essentially t minus 3 times u of t minus 3. To the right. The whole ramp function translated to the t equals to 3. Okay? Any other?
151E.
151E. Find and sketch the odd and even component of the following. 151E. Cosine omega 0 t plus theta.
The shift, man. The shift of coast.
There are 2 ways how we can approach this. Let me first do a textbook way and see. Later we're going to try it a little bit differently. Hopefully you get the same result. 1,5-1. So x of t is given as cosine omega 0 t plus theta. And it says find even and odd part. Even part of function is going to be 1/2 x of t plus x of minus t, taken in the bracket. So this is how we get the even part. This is what we proved in the general case, regardless of what x of t is. So in this case, this becomes 1/2 cosine omega 0 t plus theta plus cosine of minus omega 0 t plus theta. Since the cosine is an even function, I can write this as 1/2 cosine omega 0 t plus theta, and then plus cosine omega 0 t minus theta. So that's what we have. How does the even part look like? Now you can try drawing this, but we can take one step further, I believe. There are formulas that says cosine of alpha plus cosine of beta is what? We should be able to express that as sum and
2 times cos sin
No. Say again?
Yeah.
Is it given in the book somewhere?
Cos of this beginning with 2 times.
In the beginning?
That's
Can you tell me the page so we can, or just read it? Okay. I forgot where it is, so can you teach me? Okay.
I see, cosine.
I can't find it. Where is it? Page 50, but I don't, thank you so much.
There's a page 50, but I don't
But I don't see the identity. It goes by time, it goes
You have to divide both sides.
Let's check his Wi-Fi.
It's cosine.
All right, well, let's do it this way. This one's missing, but we can do it this way. This is equal to 1/2 cosine of this is cosine omega 0 t cosine theta minus sine omega 0 t times sine of theta. And then this one is cosine omega 0 t cosine of theta plus sine omega 0 t sine of theta. Right?
right.
Now, these two cancel, and then these two are the same. So this is just cosine of theta times cosine omega 0 t. So that's an even part. Okay? Now, odd part is going to be 1/2 x of t minus x of minus t, right? And then going through the same motions, really you end up this, you get minus minus, so it will end up being minus sine of theta sine omega 0 t, right? So that's a odd part, this is an even. That's how you can do it by utilizing exactly the definition in the book. Another way of doing it is you can say something like this. X of t is equal cosine omega 0 t plus theta, which is cosine omega 0 t times cosine of theta minus sine omega 0 t times sine of theta. This is even, and this is odd, right? Which is essentially the same result. Okay.
There's four terms in this one on the left?
No, there's this is ending like this.
Okay.
Right, sorry. Hmm?
Yeah,
Trigonometric identity.
Trigonometry.
Yeah, yeah.
You will
Which
get
one?
like a sine and cos wave for the result, even
Yeah.
more.
Next one. Any other?
Let's move to
Do we have to do 1.5
Let's
11?
chapter 2 and
1.511. Let's check it.
You said we have to do 1.5 12.
What page is that?
145?
Professor 243.
1.511.
243.
Figure 11 plots a complex signal in the complex plane over the time range. 0 time corresponds with a complex over even signal. 1.511.
No, no,
Okay. In the complex plane, plot WT over if even signal, odd signal, conjugate. Okay, yeah. This, try to do this one. All right, do you want me to do it or? Why don't you try it? It's actually, have you tried it? I mean, or you just gave up?
I was at a loss.
All right, so let me at least start, right?
yes, sir, fine.
I'll be So here's where we are somewhat constrained by living in 3 dimensions, right? Because this is like essentially the problem is 2 dimension. The problem is 4 dimensional, right? So here's what happens. This is the real, and this is imaginary. And this is how the signal looks like. This is 1. This is 1. This is 2. Now, this is a signal W of t for t between 0 and, let me just leave some space here. So this is W of t when t is between 0 and 1 inclusive. And one thing that you notice right away when you look at this graph, there's no t, right? There's no t. So how do you understand this graph? Well, at t equals 0, this complex function starts at here, and then at t equal to 1, it ends up here, right? So, there are, what can I tell about the real part of this function? So this is t now, and this is a real part of W of t. It gets to real part, so this is the motion along this axis, right? And let's call this t1, and this time here is 1. So in the first part of the trajectory, the function moves from 0 to 1 on the real axis and from 0 to 1 on the imaginary axis. So if I were to plot this, this is how it looks like. On the real axis, it goes from 0 to 1, and then on the imaginary axis it goes to 0 to 1. Right? Now, after a certain time, the motion along the imaginary axis stops. So the imaginary one stays constant at 1, and this one goes from 1 to 2. This is 2, this is 1. So this is one possible way how this function may look like if you give it a real part and imaginary part. Okay?
Sir, how will we calculate the slope of from 1 to 2 for the real part?
That's the ambiguity here. You don't know, right? If the motion, let's say one simplest way of writing this is to assume that the motion along, for example, a real axis is constant, then the slope is constant, right? But it never says in the problem that that's the case. So I could have been moving from here to here over, let's say, 1.9999, and then get from here to here in no time, right? So that's the ambiguity. I didn't see that he specifies anything. So there is nothing that anchors the point at which you are. It says just that at 0 you are at origin, and at 1 you are at this end point. But how did you get here? You know, it doesn't say. Also, I didn't really have to move in a straight line. I could have moved, let's say, another solution would have been looking something like this, right? Would have been? No, no, because I'm moving along the main diagonal, so I have to be moving the same way. But I could have done this, and this one could have been like this, right? Right? Kind of starting slow, and then speeding up, and then really too fast, right? There is no one solution to this. Now that you have the real and imaginary part, let's call this x of t, and let's call this y of t. So you have that w of t is equal x plus t plus j y of t. So the condition for even signal is that w of t is equal to w of minus t, right? And then that means that x of t plus j y of t has to be x of minus t plus j of y of minus t. Okay. Now, if that's the case, then both of these need to be even functions. Then meaning that the real part needs to look like this, and then imaginary part should look like this, right? So you were at, you're coming from where? You have to be
minus 2 to 1. Minus
let's see. At minus 1, this is where you were. At minus 1, you were at the same point, right? T equal to minus 1. You were at the same point. And then this one stayed for the imaginary part stayed constant, and then both of them you ended up at 0, right? So this is the motion in the real part, right? And then you come back here, right? So that would have been for even, and then for odd, you just need to make these functions odd and get there. Now, I'm not sure that this is an even condition. Maybe there's some complex conjugate there. Look at the definition. You know, but this is how you work with this problem. Okay.
Yeah, I'd like to ask about this. There is another review for chapter 2, or just for this review before the exam?
No, there will be this review, and then we'll have another review, and then review for the exam. So there will be 2 more sessions before the exam.
So you,
The exam is going to be in October, like 10.
Let's talk about it next time, because I'm not prepared. I haven't thought through it. So I'll think about it, and then next time we'll discuss it.
you guys are
So
supposed to
this one,
review now?
This will be posted as video. There will be no,
And the one you have on
and the one I have will be posted just as a PDF. So you'll have both.
just today focus with chapter 1 only,
No, this is kind of whatever you gave me, I saw.
but it's already done.